So, with this video, we're going to be focusing on Newton's third law, which is a little different than the first two. So, let's review. So, Newton's first law states that an object at rest will stay at rest as long as the net force is zero, or an object moving with a constant velocity will continue moving with a constant velocity as long as the net force is zero. We're dealing with equilibrium. And here's the thing, we're focusing on an object at rest. So we're looking at one single object. Newton's second law says an object, its acceleration is directly proportional to the net force and inversely proportional to that object's mass or inertia. This is dealing with situations where we're not in equilibrium. Net forces cause things to accelerate, okay? But Newton's second law is also just focusing on an object. An object's acceleration is directly proportional to the net force and inversely proportional to that object's mass or inertia. So the first two laws focus on an object's motion, okay? The third law is a little different. It's the interaction between two objects. And it states for every action force, there is an equal and opposite reaction force. So I want to point that out here. So this is the interaction between two objects or a pair of objects. Okay. I also want to point out that these action-reaction forces don't balance each other out. So the action force and reaction, and I'll explain what that means here in a little bit, force don't balance each other out. Don't. Okay, another thing here is the action and the reaction force are the same type of force. So the action and reaction force are the same type of force. What that means is if the action force is an applied force, the reaction force is also an applied force. Or if the action force is a gravitational force, then the reaction force is also a gravitational force. So I've got lots of examples that I want to look at. So remember, we're dealing with a pair of objects. Okay, so let's look at the tennis racket. So here we have the tennis racket, and then we have the tennis ball. So we're looking at the reaction and action, or the interaction between these two objects. So this is the force here of the ball on the racket. This right here is the force of the racket on the ball. And according to Newton's third law, for every action force, there's an equal and opposite reaction force. So the force of the racket on the ball and the force of the ball on the racket are equal in size, but opposite in direction. Okay, two objects, racket, tennis ball. The forces are equal and opposite. They're the same type of force because the force of the racket on the ball is an applied force, and the force of the ball on the racket is an applied force. Okay? The big one here that students always get confused with is they don't balance each other out. So here, these are two different forces on two different objects. When we're talking about forces balancing out, we're looking at the forces on a single object. Okay, so for example, we have a person standing on the floor. Okay, we know that there's a gravitational force and a normal force acting on that person standing on the floor at rest. That's the free body diagram. Both of those forces are on that person. We would say that these forces balance each other out because they're both acting on that one person. These forces, this force is on the racket. This force is on the ball. Those forces don't balance each other out because they're on two separate objects. Let's continue. Here, right? This person pushes on the wall pushes on the person. Okay? So we have two objects. We have the ghost or the person. So we have the person here, and then we have the wall. This is the interaction between those two objects. We've got the force here of the wall on the person, and then we have the force here of the person on the wall. So force of wall on person, force of person on wall. Those forces are on two separate objects, and they are equal in magnitude but opposite in direction. Now, this is where it gets a little tricky because people say, but wait, the wall's not going to accelerate, but the person is. Okay, so you have to remember the acceleration of an object, according to Newton's second law, is the net force divided by the mass. So yes, the force of the wall on the person is equal to the force of the person on the wall. But the person and the wall don't have the same mass. The wall is attached to the earth, which has a large mass. So we wouldn't expect the earth to have a big acceleration, whereas the person's mass is smaller compared to the wall or the earth's, and so we would expect it to have a bigger acceleration. But the forces are equal and opposite. Okay, rocket and launching. This one's a hard one. So in this case, the two objects, we have the rocket and then we have the gas. All right? The gas. So we have the force of the gas on the rocket, and then we have the force of the rocket on the gas. And those forces are equal and opposite. Okay, two objects, right? Forces are equal and opposite. They don't balance each other out because you've got the force on the rocket and then the force on the gas. They're the two different objects. The forces are in two different objects. Let's look at this one. So here you have the book and the earth. There's your two objects. You've got the force of the earth on the book, and you have the force of the book on the earth. Okay? Those forces are equal and opposite. They don't balance each other out because this force is on the book, this force is on the ground or the earth. Okay? In this case, I would call those like gravitational forces, maybe. Like you've got the gravitational force of the earth pulling down on the book, and you've got the gravitational force of the book pulling up on the earth. You could also think of maybe as a normal force. Okay? Oh, this one's a good one. So the tennis ball and the earth, two objects, tennis ball, earth. You've got the force of the earth on the ball. You've got the force of the ball on the earth. Equal and opposite, two objects. In this case, this is a gravitational force, and this is a gravitational force. So The Earth has mass, the ball has mass, they're gravitationally attracted to one another. Now, this is hard for students to wrap their heads around. The Earth is pulling down on the ball. The ball is pulling up on the Earth. Those forces are equal and opposite. But why do they have different accelerations? But again, you have to remember the acceleration is the net force divided by the mass. So the ball is going to have a bigger acceleration because it has less mass. Even though the force on the ball, the force on the Earth are equal, the Earth is going to have a smaller acceleration because it has more mass. I mean, we've got so many here. The moon orbiting around the Earth. Okay, so here, this is the force of the moon on the Earth. It's a gravitational force. This is the force of the Earth on the moon. It's a gravitational force. Those forces are equal and opposite. Now, are they going to have the same acceleration? No, because the moon has less mass compared to that of the Earth. Okay, Newton's third law: for every action force, there is an equal and opposite reaction force. Two objects. Those action-reaction forces are the same type or kind of force. They don't balance each other out because this force is on the Earth, this force is on the moon. When we talk about forces balancing out, we're looking at forces on a single object. All right, that's it.